All right. Hello, everybody. I would say good afternoon. Well, maybe you can see my time. That's my time right now. It's 12:23 on Tuesday, August the 17th. But welcome to another installment of Did You Know? Calculus Style. I do apologize again that you have to deal with me. Okay, so in this section, one of the things that we are going to be looking at is left hand and right hand limits. So as things come in from the left side or as they come in from the right side. This is just like in pre-calculus when you would have to make the statement like, as x approaches -1 from the left, f of x approaches, and whatever it approached, right? That was made in chapter 2. I believe we did it later on as well. But this is stuff that it's not necessarily new to you, other than there also being the limit involved, right? So that limit involved is that as x is approaching, f of x is also approaching whatever it is approaching. So this -1 from the left, that's what that means, that I am coming in from the left side, from the negative side, and moving to the right with my y values and seeing what they are approaching. So as I approach -1 from the left, it looks like my y values are going to 2. So I would say this is equal to 2. As I approach from the right, so that is following my function this direction and getting closer to the y value there, which is 0. So this limit is equal to 0. Now, for the overall limit to exist, in order for that to happen, like we've been saying verbally, the limit from the left has to be equal to the limit from the right for there to be equal to a overall limit, kind of like -1 from either side. But since this is not the case here, so that's not true, this limit does not exist. Okay, so that's kind of the idea of one-sided and two-sided limits. Two-sided limit is just our overall limit. One-sided is from either the left or the right as we go. Okay, so the next thing that I want to get into with you guys is proving that continuity exists. So in order to prove that continuity exists, I must show all three of these things. It may seem kind of silly to show the first two because the last one implies that the first two are there as well, but they do ask for all three statements to be made in order to prove that something is continuous. This IFF is intentional because that stands for if and only if all of these things are true. So only if all of these things are true, then I'm continuous at some value for x equals c. C is some arbitrary number, could be 2, could be 4, could be -1, could be -37, whatever you want it to be. Right? It doesn't really make a difference what it is some value of x. Okay, so let's look at a continuous function. F of c exists, so there is a point. Let's say this is c. The limit also exists. Let's see. All right, so the limit exists, and they are equal to each other because this last statement down here, if I move that, no longer am I continuous. They have to go to the same y value that the limit is approaching and the same y value that that function actually has there in order for this to be able to work out. So there must be a point, the limit must exist, and they must equal to each other. If you can show all of those things, then you are continuous at x equals c. All right, so let's take a look at how we use this in an example. So to discuss the continuity at each value of t of x, here's my function t of x. It is a piecewise function with all of these parts involved. So let's see, at -1, I am going from that part, from 3x plus 2 to 2. Right? At -1, it is only included in this part of the function. But for my limit to exist, it must approach the same y value from both sides. So I'm going to have to kind of use both there. So let's see, t of -1. Let's see if it exists. And it should. So I will plug it into these bounds. So I would have -3 plus 2 will be -1. So that part exists. Now the limit t approaches -1 of t of x. Oops, not t approaches, x approaches. My B. Okay, limit as x approaches -1 of t of x. So let's see. As I go in from the left, all right, 3 times -1 plus 2, like we said, that was -1. As I go in from the right, though, it's 2. So they're not going to the same y values, right? So that I have 3x plus 2 is something down here. And then y equals 2 is something like this. All right, so that is not continuous because this limit does not exist. So therefore, that's what those 3 dots right there mean. Therefore, t of -1 is not continuous. And that would be our statement. You don't necessarily have to write the first part. I was just going in order to kind of show you how the point continuity can work for that, making sure that there is a point there. But definitely, you need this statement as well as telling me that it is not continuous there. But again, I'm not looking for the first part, because if you can prove that one of these parts is not true, then it is not continuous anyways. So it doesn't really matter. Okay, t of 0. So now t of 0 only works, oh, that's not what I want, come on. So t of 0 only applies to the middle part, which is a line y equals 2. It's just something like that. So this should be continuous, so all I need to do is say t of 0 exists, and it is 2. The limit as x approaches 0 of t of x is also exists. And those two things are equal to each other because t of 0 is 2. The limit as x approaches 0 of t of x is also 2. Therefore, t of 0 is continuous. And that's it. All right, t of 2. So at 2, it is important to note that you are going from the middle part to the lower part because that is where our bounds are changing. You're going from 2 to 2, well, inclusive of 2 to non-inclusive of 2, really. But so t of 2 exists. T of 2 is 2, right? So it only applies to the middle function there. So t of 2 exists. And the limit as t, did it again. Oh no, don't do it. X approaches 2 of t of x. It needs to approach from the same thing from both sides. So as I approach from the left, it is 2. As I approach from the right, I would have to put in 2. So 2 minus 2 squared plus 2 is 2. So that one is cool as well. So it approaches 2 from both sides. So therefore the limit exists. They are both equal to 2, t of 2, and the limit as x approaches 2 of t of x. Therefore, t of 2 is continuous. And that would be what we're looking for. Okay. So types of discontinuity, there are really only 2 types of discontinuity that we are going to talk about in calculus. This is all they're going to test you on the AP test. I think our book asks you if it is like infinite or oscillating, stuff like that, but I'm not really looking for it. I'm just looking for whether it is removable or whether it is non-removable. Those are the only types of discontinuity that we are going to talk about. So if something is removable, the limit exists. All that means is I had a hole, the limit still exists, but that point was removed. Non-removable, the limit does not exist. So that is something like an infinite discontinuity, things like that, or if it's jumping, or if it's oscillating like we saw with sine of 1 over x, where it's just like, hey, yeah, I don't know what's going on. Yeah. Right. So at certain values, different discontinuities can happen, but I only care whether it's removable or non-removable. That's it. All right. So here we go, discussing improving the continuity when x equals 2. So again, my steps that I'm looking for. G of 2, does it exist? Yeah, is 5/4. G of 2 is 5/4. The limit as x approaches 2 of g of x. Oh, don't say it equals 5/4. Come on now. Although I guess you could do that. You could do that too, because g of 2 equaling 5/4 implies that it equals a number, implies that it exists. That's fine too. Okay, so the limit is g of x as x approaches 2. So now the deal with this, no! What did you do? Stop it! Sending all these staff meetings. I don't want to go to your staff meeting. Let's skip them. I'll probably still go. Okay, so as I'm approaching 2, the deal is it's not where I am right at 2. It's what I'm doing, my behavior as I approach 2. So I need to use that part of the function for this g of x. So the limit as x approaches 2, gets really, really close to 2, would work with the top part of the function. So I would do x plus 3, x minus 2. I'm factoring it just because it is quadratics, and factoring sometimes reveals things that I need to think about anyways, as it does in this case. Because my factor x minus 2 would divide out, so my limit now, if I put in 2, would be 5 over 4. So that also exists. And g of 2 equals the limit of x approaches 2 of g of x. Therefore, g of 2 is continuous. Stop it. My goodness, go away, people. All right. So that's all that I would be looking for there. All three statements, the 1, 2, 3, and then telling me whether it's continuous or not are what we are going to be looking for. Okay. Find the values of a and or b. I said and or b because of part b, such that f of x is continuous. So with this first one, for it to be continuous, again, I have to have a point, and the limit must approach for the same thing from both sides. So here I'm going to have a point because it's inclusive right there. And really, x equals 1 is my issue. If I have a break, my break is going to happen at x equals 1. My 3x squared is just a quadratic, so that's cool. My ax minus 4 is just going to be a linear function, so that's cool. So my break happens right there. So what I would like to do, f of 1 exists. Now I need to show that the limit as x approaches 1 is the same thing from both sides. So what that means is if it's the same thing from both sides, when x equals 1, they need to be going to the same y value. So if I say when x equals 1, then 3 times 1 squared must be equal to a times 1 minus 4. They have to go to the same value. So that means 3 equals a minus 4, and a would be 7. And that's it. That's really all there is to it. Because 3x squared is a graph that looks like that, less than 1, so I'm here. And then 7x minus 4 is what this really is a line with a y-intercept of negative 4 that has a slope of 7, so up 7 over 1. But it's going to fill in that circle, because if I put in 1, then it's really 3, and then I will continue my slope of positive 7. So that's what that function would look like now. But you're just trying to find where at the breaks such that both of these functions connect to each other, even though it's all one function. Both of the parts of the function connect to each other. Stop sending me invitations. I don't want to go to your party. Party, not potty. Okay. That's kind of, okay. I'm just going to shut up. That got weird real fast. Okay. So here, my breaks are happening at negative 1. I also have one happening at x equals 3. So those are kind of be my two places where I need to make sure that this linear function in the middle connects to the 2 and to the negative 2. So I would say when x equals negative 1, it's going to make me come up with this function, 2 equals negative a plus b. So when I put in negative 1 for x, the other place would be when x equals 3, I would have negative 2 equals 3a plus b. Okay, this part over here, I'm probably not really going to write. I'm just trying to help you see where I'm getting those values and those functions. But if this helps you to have it, you're more than welcome to have it as well. So now it's dealer's choice. It's whatever you want to do, however you want to solve this thing. You have an a, you have a b that you are trying to solve for. So personally, I like elimination. So I would multiply the top function by negative 1. No, she sent another invitation. Why you gotta do this to me now? You like my song? I know you like my song. It's okay. Oh, you're clapping for me? Oh, that's just too much. Okay. All right. I can't imagine what people would think if they just saw me doing this. Like, there's nobody sitting in my room right now. It's just a blank classroom. It's very boring. But I just imagine like a third person just watching me make videos and talking to my iPad and just talking, not another meeting! And what they would think. Probably think, like, isn't that a crazy person? I don't know. Anyways, a equals -1. So since I know what a is, I can substitute it. I would probably choose to substitute it there. So I have 2 equals 1 plus b, which would mean that b, that's another comma, that b would be equal to Juan. Alrighty. Okay, so next thing, this intermediate value theorem down here that we're going to so handily talk about. It's kind of an old thing, but what it is say I have some x equals a and some x equals b. And I have some continuous function, doesn't really matter what it is, but if I have the y value f of a and the y value f of b, then, stop it, my goodness. I must, at the bare minimum, go through every x value along the way. I know that wasn't the path of my function goes here, but say I had f of a was equal to, I don't know, 4 or something, and f of b is equal to 8. Then if I'm talking about on the interval a to b, my function, or there must be some value c, f of c, then f of c must exist somewhere between 4 and 8. It can be inclusive of those as well. F of c is an element of anything between 4 and 8. So it is essentially saying, if you're given 2 x values, and as long as I can say that this is a continuous function, then I must have all of the y values between the y values of my endpoints. That's all that the intermediate value theorem is. Intermediate is kind of middle, so it's the values in the middle of my bounds. So here is the formal definition. If you want to pause the video, copy it, you're more than welcome to, but that's essentially all that it is saying. A continuous function, some function name, there must be all y values between a and b on the interval ab. Right, so these are the y values, f of a, f of b. And then it also says, if y naught is between those two values, then there must be some value of c, or x, essentially some x value, c, that equals that y value between those two on the interval a to b. So let's see how we use this. Again, any questions, please come in person, ask them, send me an email, whatever you need to do, but ask questions. I know there's always some questions on this stuff. I can't anticipate all of your questions, so please, as you guys are going through these notes, if you're refreshing, if you're taking these notes for the first time, whatever you're doing, write your question off to the side and come let us know. Okay, so for this one, use the intermediate value theorem to show that the polynomial has a 0 on the given interval. And this is what they actually used to use this for. I know this factors very nicely, and it would be easy to find what my value of x is, that my function is 0. But they weren't always so nice. And mathematicians would find 2 y values, say they would find 1 down here, 1 up there, and their function did something like that. I don't know. But they would say, hey, that's -2, hey, that's 8. Well, what if I move my value of x closer? What if I move it closer and closer and closer? So eventually they would move it close enough that they would be able to actually find their 0. But we're not going to be necessarily doing that right meow. Okay. So using the intermediate value theorem to show that the polynomial has a 0, so that my function is equal to 0, my goodness, on the given interval. Here is my given interval. So these statements, I'm always going to start out the same way, because really what I want to show, if that I have to equal 0, is that my lower number is less than 0 and my upper number is greater than 0, or vice versa. So let's just see how the numbers work. So since f of 0 equals, let's see, that would be 8, and f of 3 equals, let's see, 9 minus 18 is negative 9 plus 8 is negative 1. So that's what I'm looking for. That is nice. Now intermediate value theorem is in play. It's cool because if I'm going from 8 to negative 1, that means somewhere along the way from 8 to negative 1, I must have gone through a 0 in order to get there. That's essentially what the intermediate value theorem guarantees. So since this is true, f of c equals 0, because that's what I'm looking for some c. You can write x equals c if you want to, on 0, 3, and then state how you know it by the intermediate value theorem. My goodness. By the intermediate value theorem. So on this question, I will award you 3 points. 1, 2, 3. Right? So how you know, what you know, and why you know it. Cool. So that's all I'm really looking for. If it didn't work out, say f of 3 was 3 or something like that, then f of c could, could equal 0 for some c, but it's not necessarily guaranteed. More so how I see them asking this question would be like in a multiple choice question if they have like 3 parts. Stop it! And they would be like, tell us which one of these is true based on f of x on the given interval. And it'd be like one of them is f of c equals 4 by IVT. Or something like that. And you'd be like, is it true? Is it not? And you'd have to check your endpoints and see if you can equal 4. So most likely you're not going to be given one that is not true if it is a free response type question. But we still need the proof that it is true. I think this was negative 1, blah, blah, blah. Yeah, you should have it. You'll be able to rewind and see that statement. Okay, for our 5th one, prove the polynomial contains f of c equals 4 on the interval 0, 2, 3. My goodness. So, since f of 0 equals negative 2, hopefully I'm bigger than 4 on this next one. And f of 3 equals, let's see, 27 minus 9 is 18, plus 3 is 21, minus 2 is 19. Then f of c equals 4, because 4 is between negative 2 and 19. For some c on the interval 0 to 3 by intermediate value theorem. It's not always the interval 0 to 3, but you guys will see that as you work through your homework as well. Okay, the next ones are going to be left and right limits, but actually seeing them in an equation or in a limit, in an expression. So let's see, on this one, if I can do direct substitution, I will do it. And that is always going to be my go-to. However, if I put 4 in my denominator, that's 4 squared, so 16 minus 16 is 0, so that will not work. Dang! But let's see if we can rewrite it, because I see a quadratic in my denominator. Well, I'm almost there, right? These factors are kind of close, but the signs are the opposite. So if the signs are the opposite, I could factor out a negative. And now, oh, happy day! Right, x minus 4 divides out x minus 4, so I'm left with negative 1 over x plus 4, which is negative 1 over 8. And that's it. All right, next one. So one like this, you will probably be given a calculator, but even if you're not, we can still think about it. So I am approaching negative 4 from the left. So if I put in 4, it's not going to work. No bueno. However, I'm really thinking that I'm putting in like negative 4.1, negative 4.01, negative 4.001, so on and so forth. So whatever number I have will come out the same thing as it is up top. But this will be like, I don't know, what is 4.1 squared? Oh, 1861, 16.81. Stop. Oh my gosh, you're so annoying right now. All right, so that'd be 0.81. The square root of 0.81. So that'd be a small number. But moral of the story here, and really the thing that I'm trying to get through to you, is that the numbers are going to be getting smaller. The difference in the denominator is going to be getting smaller. So if the denominator is getting smaller, as in if I have something like 4 over 1 over 100, and then I go to like 4 over 1 over 1,000, the number altogether is getting bigger. Right, so 4,000, right? So 4 over 1 over 100 is smaller than 4 over 1 over 1,000. That one's much larger, right? And the only thing that's different about this than my example is that I have negatives in my example. So I'm going to a very, very large negative number. It's increasingly negative. So this one is going to negative infinity. So kind of this is one that we can think about how the numbers work. But you can see on a graph as well, for sure, that it is going to negative infinity there. Okay. Last one. We're almost there. You're gonna do it. We're gonna get all the way through the notes. Okay. Limit as natural log of 6 minus x approaches 6 from the left side. The natural log of x, if we do not remember, that is okay, is a graph that looks something like this. It's kind of like a man that is running, he's running, and he's going to jump over a log head first. Okay, but there's natural log. Now, in order to get the transformation of this thing, I would want to rewrite this as ln of negative x minus 6. So that I see the negative out front. What that's doing is it's taking positive x values and making them negative x values, so it reflects over the y-axis. And the x minus 6 moves everything to the right 6. So that graph reflected over the y and then moved right 6. That means I have an asymptote at x equals 6. And I have a graph something like that. So as I approach 6 from the left side, I'm following along there, and I'm going down forever. So this will also be negative infinity. All right, that's all I got for you guys today. Whatever questions you have, please feel free to ask, and we will talk to you all soon.